So we're going to begin our next unit, which is Unit 4 on chemical reactions. We have a bunch of different reactions that we're going to talk about. Double replacements, net ionics, things that we talked about in regular chem. And then we're going to introduce towards the end something new, which is a redox reaction. And it'll actually answer the question, what is an oxidation number and why do they call it an oxidation number on your periodic table? We use those when we were trying to name and write formulas for ionic compounds. So we'll be able to get into all of that towards the end of this unit. So we're going to be looking initially here. Topic 4.1 discusses evidence of a chemical change, physical changes versus chemical. We'll talk about those. We'll talk about representations of reactions, which are essentially your chemical equations, and discuss what happens with those as far as particulates are concerned. So difference between a physical and a chemical change. Chemical changes do not chemical changes do change the identity of the substance. Physical changes do not. So physical changes, color, odor, density, hardness, solubility, melting point, boiling point, all of those are evidence of chemical properties. Physical properties. Chemical properties are exhibited by substances and they react with other substances. So, for example, if you take hydrogen gas and oxygen gas and you give it some activation energy, we're going to create water. And then likewise, we can take that water and we can go through a process called electrolysis where we can get back the hydrogen and the oxygen gas. Flammability, corrosion, those sorts of things are chemical properties. We will also be talking about chemical properties in relation to acids and bases, something called oxidation and reduction, which is called redox. That's the oxidation number that I was talking about earlier. We'll be discussing that. And then changes which the physical or chemical properties of the substances are altered. Those are considered your physical or chemical changes. So physical changes, some aspect of the physical state of matter is altered. So all phase changes, boiling, freezing, melting, all phase changes are physical changes because you're not changing the chemical composition. You're just either reducing or increasing the intermolecular forces. And that's what's causing the change. But the actual chemical composition of the material is not changing at all. The most common physical changes are changes of state. These then are summarized over here. So like I was saying, all of these are physical changes. We are not dealing with a new substance. We're just simply changing or altering those intermolecular forces. So chemical change then, you're going to have a chemical reaction. The atoms of the substances are going to be rearranged. Chemical change then requires that the new state or substances formed have a different chemical composition. And chemical changes are often accompanied by observable changes such as color changes, odor, gas production, energy changes, fire, light being given off, heat. So heat either gained or lost. So there's a lot of indicators of chemical change that we're able to see. Evidence for chemical change can be seen in a bunch of different ways. This is what I was just saying on the last slide. Heat, light, color change, formation of a gas, electrical current, which we'll get into in our last unit. And these changes are sometimes called driving forces. So here's some gas-producing reactions, kind of a generic one where we have acid.
Victor Jose, please come to the Student Center. Victor Jose, please come to the Student Center.
Acid and metal, you're going to form a salt and hydrogen. You can put a splint to it, and it gives you kind of this pop, squeaky pop kind of sound to it to be able to hear that hydrogen gas was produced. Acid and a carbonate is going to give you salt, water, and the carbon dioxide. So this is going to be your gas that's formed. And the splint will actually go out because of the CO2. CO2 is oftentimes one of the things that they put in fire extinguishers because it does extinguish gas or extinguish fire. Production of oxygen then by the decomp of hydrogen peroxide. So that's going to relight, the oxygen will actually relight a glowing splint. So the splint has to be glowing in order for that to happen. So if you remember the activity series, when I taught that to you in chemistry, we talked about like football and a roster and how like something on the activity series that's lower won't replace something that's higher. And we'll talk about that when we look at a couple of reactions here coming up. But some of the metals will react with water, some with acids, some with both. And then you can make predictions of that using your activity series. You do not need to have the activity series memorized for the AP exam. Again, metals are arranged according to their ability to displace hydrogen. Most reactive are on top. Your alkaline metals tend to be towards the top, and stuff like silver, gold, things that don't react with water tend to be towards the bottom. And if you think about the things that that we have in real life that interact with water and don't corrode, that's an easy way to kind of build an activity series in your mind. So I think you know, a lot of you have seen like a demonstration with lithium or potassium, and they put it in water and it goes crazy and reacts, as opposed to like the copper pipes in your house or the gold ring that might be on your finger when you wash dishes. The thing doesn't go away, it stays there. So you can see kind of the activity series in your mind when you think about real life substances. So here are some examples of different metals and how they're going to react, and you determine whether one will replace the other by their appearance on this activity series. So if you have, for example, zinc nitrate and iron comes along, zinc nitrate is not going to react with that. But if aluminum comes along, it'll replace the zinc and become aluminum nitrate. So here's just the rest of this with hydrogen. You can see that these metals here, they end up having no reactivity with hydrogen. And when you look at this, you can see these are a lot of these are considered precious metals. And then you've got copper. And if you have a home that was built like in the 80s or 90s or earlier, you probably have pipes in the basement that are made of copper, because copper tends not to react with water. And so that made that a good choice for using for pipes in your home. So activity series then is used to predict if a metal will be oxidized by an acid or salt. And you arrange that in decreasing ease of oxidation. And our active metals, the alkali metals, come first. Then we have alkaline metals. Then we have noble metals, which are essentially your gold, your platinum, that sort of thing. Okay. So any metal on the list can be oxidized by the metal ions of elements below it. If only metals above hydrogen are able to react with acids to form water or hydrogen gas. All right. So here's some practice. We've got copper does not react with HCl, but will with nitric acid, because copper too is oxidized by the nitrate ion. So you can see here we've got some equations here where we've got our copper. It's going to be, the copper is going to go in with the nitrate, and then we're going to form water and NO2. And then magnesium here, magnesium's here, iron's here. Magnesium's higher up on the list, so it's going to bump iron off, and magnesium's going to come in and sit here. All right, particulate diagrams then are something that you will oftentimes see on the exam, where you have to be able to determine, looking at the diagram, possibly like which one is the limiting reactant, which one are you going to run out of first, and then you'll be able to kind of see what is formed and how many moles of each thing can be formed. So for example, here if we had hydrogen gas and oxygen gas, they could go and form 2 moles of water. And so sometimes they'll make you write a balanced equation for it, that sort of thing. Okay. So chemical equations, shorthand method, and they illustrate what happens during a chemical reaction. There can be a number of steps to writing them. First, write the equation in words. I would not waste my time doing that. Fill in the correct formula for all the substances and then balance the equation. You do not have to add the symbols in for state. They're not always necessary, and you don't have that kind of time on the AP exam. Okay, so make sure that when you're doing this, that you're using the correct formulas for your reactants and your products. Balance each element in turn. Remember, you can keep polyatomic ions together. That makes things a lot faster to balance. We talked about that in regular chemistry. If an element appears in only one compound on each side of the equation, try balancing that first. And if one of the reactants or products appears as a free element, try doing that one last. So remember, I always talked about single atoms, leaving those behind, wait until the very end to balance those. And then when balancing, only place numbers in front of the whole formula. Don't change the subscripts ever. The numbers that appear in front of each formula are called the coefficients, and they have an extremely important role to play when we come in and start doing stoichiometry. So let's look at some equations that we need to balance here, and you can see if you can come up with the correct answers for these. So take a minute and run through these two examples, pause the video, and then come back for an explanation. All right. Did you remember that hydrogen was a Brinkelhoff? All right. So then we need to balance, and it looks like this guy's already balanced. So carbon, oxygen is a Brinkelhoff. So we need to get this to balance. I need to put a 2 here and a 2 here, and now I've got it balanced. Magnesium, sulfuric acid. Hydrogen is a Brinkelhoff. Okay, and everything's balanced for that one. All right. Reaction between hydrogen gas and oxygen gas can result in the formation of liquid water. Describe any observations that you might reasonably expect to make during this reaction. So we're taking these two things. So we're going to go from gas into a liquid. That would be something that we would see. You would probably see some sort of condensation formed as well. And then we're taking H2 and O2, and we're going to combine them into water, and then we need to balance, and now I've got it balanced.